Look closely at a bat in its most natural state, fast asleep, hanging completely upside down from a sheer surface. For most creatures, maintaining a grip like this while unconscious would be impossible. Gravity should eventually pull them to the ground. This isn't a lightweight bird. It's a mammal. It has hair, it produces milk, and it carries the solid bone and muscle weight typical of its class. Staying airborne and resting in high places usually requires the low-density, hollow-boned anatomy of an avian body. To find out how a heavy mammal survives in these vertical spaces, we have to look at the bat's anatomy as a collection of specialized mechanical systems. For a human or a dog, gripping something requires constant, active muscle flexing. The moment the brain stops sending that signal, the muscles relax and the grip fails. Bats avoid this exhaustion through a physiological adaptation called an automatic locking mechanism. In this diagram, notice how the downward pull of the bat's body weight creates tension on internal tendons, triggering a mechanical pivot that forces the claws to clamp shut. Because gravity itself keeps claws closed, the bat expends zero energy to maintain its hold. This allows them to remain in a deep sleep for the entire day without any risk of their legs fatiguing or their grip loosening. By utilizing its own mass to engage the lock, the bat uses gravity as a permanent, energy-free anchor. However, this leg structure is so specialized for hanging that it leaves the bat with almost no leg strength for a traditional takeoff. They cannot run or jump into the air. To fly, they simply release their mechanical lock and use gravity to fall. This drop launch provides the initial airspeed needed to fly. Those wings are unique in the animal kingdom. Unlike birds, bats have no feathers. Looking at the skeletal structure, the bat wing is an extremely elongated hand. Those long, thin bones are fingers wrapped in a flexible skin membrane. These hand wings let the bat manipulate airflow by flexing individual fingers, giving them high directional control mid-air. By combining a gravity-assisted launch with finger-driven wings, the bat converts a fall into a highly maneuverable flight path. Navigating that flight in total darkness requires a sensory system that doesn't rely on light. The bat uses a biological navigation system called high-frequency echolocation. While flying, they emit high-frequency sound waves that are far beyond the range of human hearing. These waves travel outward and physically bounce off obstacles in the environment, returning to the bat as echoes. The bat's brain processes these echoes to render a 3D map of the surroundings in under 1 second. This precision allows them to track and catch a single mosquito in pitch-black conditions. By mapping the world with sound rather than light, they occupy a nocturnal niche that few other mammals can reach. When we look at the physics of the bat's claw, the structure of its hands, and its sonar, we see how these systems fit into a larger purpose. This anatomy makes bats the primary control for insect populations that would otherwise destroy millions of dollars in crops. They also function as essential pollinators, sustaining the plant life that many other species rely on. Understanding the technical complexity of their bodies helps shift the perspective away from fear. The bat's specialized survival traits make it a cornerstone of the natural world, providing the biological services necessary for the ecosystem to thrive.